I am Dr. Nelson Stone. I am a professor of urology and radiation oncology at the Icahn School of Medicine at Mount Sinai. I am also one of the founders of 3D Biopsy, along with Dr. David Crawford and Scott Lucia from the University of Colorado. I and my colleagues founded 3D Biopsy to solve a difficult problem, which is prostate cancer diagnostics. We are not happy with the current tools, which only take a small specimen out of the prostate, which results in mischaracterization of the tumor in 50% of the patients and false negative biopsies in 30%. In addition, if we truly want to get to focal therapy where we know the exact location of lesions in the prostate, a new system needed to be developed. Working with these ideas, we have developed new products that will hopefully solve this dilemma. The first challenge was to develop a needle that would not deflect. So we designed this trocar tip, and when we tested in the lab, comparing it to other needles commonly used for biopsies, we found that this needle deflects 1/9, or an average of 0.1 millimeters when fired into a hydrogel. The next challenge was to develop a needle with a long enough core bed so we can encompass the entire length of the prostate. In other words, if I was taking a biopsy through the rectum, or truss biopsy, I would want the specimen to go from the posterior capsule to the anterior capsule. If I was taking a biopsy from the transperineal route, I would want the biopsy to go from the base of the prostate to the apex. By creating a needle with a 6-centimeter core bed, that will allow us to biopsy up to 95% of all prostates. As you can see, there are ridges along the core bed. What these ridges do is they hold the tissue in place, thus ensuring the entire length that one wishes to obtain. For example, if the length of the prostate is 5 centimeters and one wants a 5-centimeter specimen, then this will get the entire 5 centimeters. Testing in the lab with animal tissue has demonstrated that we do indeed get over 90% of the tissue that we require. The next component for the 3D biopsy system was a biopsy device. This device allows the user to dial the length of the specimen desired between 20 millimeters and 60 millimeters. This indicator shows how far or how long the specimen will be. In order to change the length of the specimen desired, the user dials the knob at the end of the gun, which will adjust the throw of the needle and the length of the specimen to be obtained. The needle is inserted into the biopsy device similar to other reusable devices. The needle will come in a sterile package with this insertion tool. The biopsy device is reusable and can be cleaned or sterilized by any number of methods. In order to insert the needle into the device, the door on the bottom is opened. You will notice there is a notch in the front and a notch in the back. These need to be exposed in order to insert the needle. On the bottom of the needle, there are 2 cutouts. These cutouts need to fit into those notches to properly insert the needle. Slide the tool forward and pull it out. Once seated, the device can be closed. The door should be pushed back until it clicks in place. Now the needle is ready to be used. This device will fire the needle into the specimen in a coaxial fashion. By lifting this lever, the cannula is retracted, exposing the core bed or the notch. When the handle or the lever is lifted and pulled back a second time, the needle is retracted into the cannula and is in its firing position. The user or the urologist will now want to adjust the length of the specimen based on the ultrasound of the prostate or using the new 3D biopsy system software. Again, adjust the length of the throw by turning the dial. Let's say, for example, we want to take a 45 millimeter or 4.5 centimeter biopsy. We set the gun or the biopsy device at 4.5 centimeters. We already cocked it twice and it's ready to go. In order to fire the gun, we need to push the safety forward like this. Now the gun is in the safety off position and can be fired. This is the Integrated Pathology System, or the IPS, that was developed for 3D biopsy. The specimen goes on this tacky Velcro pad. It will accommodate a specimen up to 6 centimeters. So once the specimen is placed here, this tacky strip is removed and it's folded over to secure the specimen like this. It then gets placed in formalin and is transported to the pathology laboratory intact. Once in pathology, because the pathology cassettes are only 3 centimeters in length, it is cut in half along this dotted line. The base end is marked here, the apical end is marked there, and both pieces are put into the processing cassette. After processing, the specimen is embedded with paraffin, sectioned on the microtome, and stained and placed on the slide. This entire process is completed without ever having to remove the specimen from this pathology device. When the pathologist gets the specimen, he can then read from the base to the apex the location of the cancer, the length of the cancer, and the type of the cancer, and this information is then uploaded into the 3D biopsy software system. Another component of the 3D biopsy system is the 3D image-guided software. This software is designed to be used for a transperineal biopsy and consists of the following components. We have an ultrasound machine with brachytherapy software that allows us to display a grid on the ultrasound screen. We're currently doing the testing with a Phantom and was specifically designed for 3D biopsy because it has 2 MRI visible lesions. This is the transrectal probe that's used for the brachytherapy applications, and we have a specially designed 3D biopsy grid that has 15 gauge holes in it to allow us to do 15 gauge biopsies through the perineum. And we also have the software application. This is the alpha version on the laptop. Eventually it will be delivered on a PC card system so the user can plug it into any ultrasound device that can do brachytherapy applications. The 3D biopsy software can be run with just a biopsy program, or it can also do fusion biopsy with an MRI. What you're seeing here is an MRI of the Phantom showing the rectum here in the middle and the prostate and an MRI visible lesion there. The patient's MRI can be loaded into the software using a USB device, or it can be connected directly to the PACS system and the file can be sent over to the program and incorporated into the 3D biopsy image-guided software. So here we have a prostate from the Phantom, and we can cascade up towards the base or down towards the apex. So the first thing to do is to circumscribe the prostate gland using the softwares. So we'll start first with the freehand tool, which will allow us to create the contour of the prostate, like this. And we'll go down to the next slice and do the same. Now I can speed things up by just doing the paste tools. Again, I can paste it. That way you don't have to keep drawing the slices. Okay, I'm done. The radiologist is going to have multiple sequences up. And when it comes time to looking at the lesion, he's going to use those other windows to help him identify and properly circumscribe or contour the lesions, which is what we're going to do next. This is made to be used in the operating room or under anesthesia, say, for example, in an ambulatory surgery center. And it's going to be the urologist or his or her technician that actually is going to be doing this component. This is up in the bladder. We're going to click urethra. And here's another tool, which is a circle. It allows us just to paste a circle on the urethra. Okay, now we've put on the prostate and the urethra. Now we got to add the regions of interest. So we can start seeing an ROI right there, PI-RADS 5. So we'll choose PI-RADS 5, and what this does is it changes the color of the lesion to correspond to the PI-RADS designation. So we're going to, again, segment it. So we'll go freehand and we'll go around the PI-RADS lesion. So the software also tells you the size of the lesion. Let's go to the second lesion, and the second lesion we'll call a PI-RADS 4, which means it'll be a different color. So let's start with the editing tool, and we'll circumscribe the lesion here. It's very small. We're pretty happy the way the software works. Again, this is going to be used by the radiologist. And then once these contours and segmentation of the lesions are completed, we're going to show how this can be fused to the real-time ultrasound when we get to that phase. Okay, now we're ready to do a mapping biopsy using the 3D biopsy software. I have the transrectal linear array probe inserted into the phantom with a 3D biopsy template attached to the stepping device. These are hooked to the ultrasound machine. Here we have a transverse image of the prostate. The ultrasound machine is linked to the 3D biopsy software, and we're going to go ahead and fuse the MRI data that we just obtained to the live image of the prostate. We need to select a study that we just used. So this is the one with the simulated prostate. We have captured the images in Axios starting at the base of the prostate and working our way towards the apex. In this case, we've captured 10 images at 5mm intervals. We are now going to align the MRI to the acquired ultrasound images. We have to pull down the images so they overlay each other. So here's the rectum, and the rectum for the prostate is down here. And so we're going to line up the images. So here we see the base, and the contours align with the prostate, and the contours align with the urethra. The apex of the gland, here you see the MRI lesion coming into place. I'll just move the contour over, and this is bringing in the contours from the MRI. Okay, the next thing we're going to do is go over to the biopsy button here. So we'll go over to the biopsy button. So if we go to settings, it gives us a number of options. You can pick the size of the needle. So we're going to use a 15 gauge needle, and then I go to generate. It's going to generate the biopsy plan. The biopsy plan showed me 21 biopsy sites. The volume of tissue removed from these 21 sites is 0.75 cc's. Now I can go ahead and look at this in 3D. I click in the 3D model. There's my prostate in 3D and all the biopsies. Here's the region of interest here. You can see the biopsy needles going through the region of interest. We're going to start with a biopsy in the left upper corner. So if I click on it here, it's going to tell me that's site 3. And here's the needle we're going to go after. So we're going to move the needle down like that to match it so we can record that position. Over here, the software says dial the gun to 48, and that will give us a 45mm specimen length. Dr. Salup is going to pull the needle back to the apex, and I'm going to align the virtual needle so it matches the position of the needle he's about to fire. I can align the prostate, I can align the needle, and why don't you go ahead and fire it now. You can see the needle has taken a biopsy of the entire prostate from the base to the apex. I'm going to pull the virtual needle back down to align with the actual biopsy site, and then I'm going to click biopsy taken. It'll change the color of the needle to white, indicating that site was taken, and Dr. Salup is going to remove it now from the patient. Okay, so we finished that site, and now we'll go back to transverse and take the next biopsy. Okay, now we've finished the biopsy procedure. We have taken 34 biopsies. This biopsy is going to be positive. We're doing this as an example. That was site 16. So 1 and 16 were positive. Let's go back to reporting. Let's go to 1. We can put in the Gleason score. So let's say this was a Gleason 4+5. So these are our 2 positive sites here in yellow. Let's go to the 3D model. Here's our lesions. If you elected to want to do focal therapy on this patient, these images can be output in DICOM, and then these axial images can be overlaid onto a treatment planning system. That's going to be the ultimate goal once the system is fully introduced, to be able to precisely identify the type of lesion and the location of the lesion to allow the physician to elect precision focal therapy or targeted focal therapy if that's what he or she and the patient decide is the best treatment for them.